All right, time to learn a bit about numerical methods. So, the end of the last lecture was starting to get into a hint of the fact that numerical methods are very important um, for control. And because controllers are computers, so if we want to talk about simulating processes, or if we want to talk about even in some controllers themselves, you have to use numerical methods to make the controllers work and the simulations work. And so, let's give this was not the right one. Let's give some thoughts about what are numerical methods. So, numerical methods are ways that you solve problems, essentially math problems, with a computer. So what it really boils down to is they're algorithms that people find. And so that's why you'll see that there's not really any one, because as you can imagine, if there's a lot of people in there finding different algorithms to solve the same problems, there can be differences between the algorithms, but that doesn't necessarily, but that means like they're all a numerical method because they're all like solving these math problems, and the algorithms can differ in important ways, and some can be better for problems than others, and some are better for certain problems than other ones. The way that they solve these math problems, so they have to find, in the end, you want this algorithm to output a number for you that satisfies your equations, whether algebraic or differential. And then based on what type of equations you have, the idea of solving or satisfying these equations is different. So when you have like a system of algebraic equations, what you might be looking for is the set of numbers that when you plug them in, they cause the right-hand side of the equation to equal the left-hand side. When you talk about solving differential equations, that's a very different thing. That means finding trajectories that have the derivatives that are noted and meet the initial conditions. So, but either way, you want to find the solutions, however that's defined for the type of problem you're looking at, using these algorithms. And so I think one thing that really comes out with numerical methods, though, is that like it can be very tempting to look at them as like, okay, this is a math problem. But I think a really good way of thinking about it is like a lot of times you've already had the math. Like the one we're going to start talking about today is like a preliminary point, so that we start getting into it with some things that are maybe a little like going back to linear algebra and just some matrix manipulations, and then how would you even deal with those in coding. And then so that's not even differential equations, that's for sure it's not partial differential equations, but it's really important to start with things like this. It's not even, we're going to do linear algebraic instead of nonlinear. So it'll provide a good foundation because it's something that can be very well characterized mathematically, and then you can see like how the algorithms are related to that. And so the thing that I think is really important, one thing that's really important to realize while looking at numerical methods is that they are not just solving a math problem. Like it's not just that, like when you do it straight up from math class. I think a way to think about it is that by looking at it, it's basically helping you structure code. And so with coding, that's one thing that I wanted to say is that I think coding is not hard in itself. Like to look at, okay, like I need to write a for loop. So there's a way of writing a for loop. You write it, there's some syntax. That's not hard in itself to figure out like, okay, like this is a for loop, here's the syntax. But the hard part about coding, especially for engineering problems, is going to be thinking about like how do I even do it? And that's the step where numerical methods would come in, or where what we're gonna talk about today with numerical methods. Because so once you learn one of these, then it's kind of tempting to be like, all right, pull whatever I just learned out of a hat and say like, here's the one, here's the linear algebraic equation one, I'm good. Use this one and I'm done. But I think like something that to think about as you're learning this is not just like learn it for the sake of so that when you see a linear algebraic equation you do this, but learn it for the purpose of being so yeah, I mean do that, but then also do think about like how did they arrive at this numerical method, because then that really helps you with thinking about structuring coding, and because every problem is not going to be the same, and so it can help just understand how do people think about coding, how do people think about structuring coding, and that's really valuable. So, all right, so that's part of the reason why we're going to start with this, okay, I'll say like simple system, but nothing in math is simple. and nothing in science is really simple. I mean, the world's pretty amazing that it works the way it does. So, but we'll say, like, compared to how much work you have to put into to do some other things, simple. Okay. So, this is going to be systems of linear algebraic equations. I'll write up one of these. So if it's like, okay, well, what is a system of linear algebraic equations? Please show an example. Then this would be like a11x1 plus a12x2 plus ... So we're allowing for essentially arbitrary largeness. Here's a1n xn. So n is here, this big N is going to be the number of variables you have. And then but you can have some number of equations. So you can have all of your variables x1 to xn in one equation. You can have them appearing in another. This is why it's a system, because you've got multiple of them that all have to hold true at once. That's kind of going back to the idea of when we were talking about solving just a minute ago. What does that mean for algebraic equations? That means all the equations have to be true at once for whatever values of these x's that you find. And so again, allowing for arbitrary largeness, we have up to m equations. So x2 plus plus amn xn equals bm. So this is a case when we have m equations. Let me erase the title here. M equations. And n unknowns. So the unknowns are the x's. So the idea, here's a system of linear algebraic equations. What does that mean? That means we have a set of equations. They're algebraic. This is as opposed to differential. So they're algebraic because they've just got like some set of terms that you can add, subtract, divide, etc. is equal to some other set of terms. So there's no, as you can see, there's no derivatives of any type. So it's algebraic in that sense. It's just involving algebra, not derivatives. It's not calculus. So then, so it's a system. They're linear because the unknowns here, all the x's, are only appearing linearly. So every time you see them, there's no like x1 squared, for example. Each of them is just, it's there on its own, x1 multiplied by a constant. X2 on its own multiplied by a constant. So that's what we say when we're talking about systems of linear algebraic equations. It's all of them at one time mean they have to hold. And so one question you might ask is like, oh, okay, well, when would this ever happen? When would I ever model anything like this? So one thought you could have is like, okay, consider that you have like what we were doing last time. The three different differential equations related to the CSTR. And then so in that case, if you were to linearize your differential equations and look for the steady state of the linearized model, that would be an example of a system of linear algebraic equations, because you have a linearized system and they're trying to set everything, we were trying to say no time variations, derivatives are all 0, so then it's algebraic. And then so is it then reasonable to expect that you might ever need to solve systems of linear algebraic equations? Yes. So then this is a good model to start looking at. So then there's a lot of different cases. So going back to linear algebra, so this is one of the really cool things about numerical methods is that they're always tied back to the mathematics. And so they're just just getting computers to try to do it for you. But it's always tied back theoretically to, and by theoretically, I mean like in the theoretical basis upon which the methods are made, they're tied back to the mathematics. So if we have n equations and n unknowns, if you go to linear algebra, then like, okay, well, depending on like, because you could write this as a system ax equals b if you write these as matrices, which we'll say in just a second. But if you have like ax equals b matrices, and the A can have like, it's not necessarily n by n, it's like some, maybe there's more rows than columns, less rows than columns, same number of columns as rows, etc. Then you can get different types of things happening. Like you can say like, oh, okay, it's like like if it's exactly equal m is n, then there's even cases within that where it's like, okay, well, sometimes the rank of the matrix is not full rank, so then it's not invertible, so then like you can have multiple solutions and then things like that. So the things that come up when you have like numbers of equations and number of unknowns is sort of how many solutions are you going to get to this, or how many possible solutions are there that all cause the equations to be satisfied at one time. So then, because there's so many different alternatives here, we're going to focus in on one case in this, but then, as I'm saying, I'm not trying to be like, this is the only way to do a numerical method. This is the one for m is n. That's not true. Of course, there's all kinds of numerical methods out there for all kinds of different problems. Just for the purpose of what we're talking about today, we're going to do the case with m is n. And also, if you think about many cases in, like the case that we were just talking about where you have your steady states, and then probably it makes sense to say like, well, the number of states I have is the number of unknowns I have, because, and I have 3 equations for the states, and then I have 3 states that are unknown. So it does make sense to say in chemical engineering, probably makes sense a lot of times, you have like m is n in a lot of problems you would consider, so this is a reasonable case to look at. So if we were to solve a system of linear algebraic equations, if you just go to it like on your own small example, so we've all done like small examples of these in the past, and so it might almost seem kind of trivial, like, okay, well, I mean, I can do this by hand. Why do I need the computer to do it for me? Because whatever, I mean, you know, I just come over here and say 3x1 minus 4 is x2. I start plugging this into the first equation, so I say like x1 plus 2 times 3x1 minus 4 is 5. Then I say like, okay, well, that gives me x1 plus 6x1 minus 8 is 5, which gives me 7x1 is 13, from which I get x1 is 13 over 7. I go back to my equation for x2, plug that in here. Now I've got x2. So why do I need the computer to solve this? So that's a very good question. Then the reason is because sometimes you might have a really huge system. So here, if we were to characterize this in terms of m, and they're the same thing right now, that's what we're considering. So if we say, okay, how many equations / unknowns do we have? 2 equations, 2 unknowns. That's pretty small, so we can do it by hand. But what happens if you start getting really huge systems? And this is definitely a reality that's going to happen. Say that you develop sets of linear algebraic equations where, for whatever problem you're solving, there happen to be 10 to the 7th, 10 to the 8th, 10 to the 9th, like on that order of magnitude, number of unknowns and equations. Now, in that case, probably you are not going to sit there with your pen and calculate all of them. You would like a computer to do it for you way faster than you can do. So, what you want to do is say like, okay, so I mean, I understand how to solve them. I can do it by hand. But now I want to think structurally about what have I done, like I followed a set of steps, like that's how math is. There was a set of steps, this is how I did it. But then you have to sort of think through like, okay, how could I write those in a very repeatable fashion where like if every time I did these steps, I would always get the right answer. And that's the way you want to think about it for coding, because your goal is to write something that's repeatable. And a lot of times it can help to write some small example, and we'll do that in just a minute. But then let me first talk about I mentioned that it was an AX equals B type problem. Just really quick to make this quite explicit. You have this A11, A21, ANN, A12, A22, AN2. And then, so this is like if you went back to that original system that I started with at the very beginning. And then you go through it, and then you would make like, this would be your matrix. And then where all these A's are known, you have this matrix B where the B's are known. So B1, B2 to Bn. Sorry, this is a vector. So it's a n by 1 matrix, but it's a vector. Here's x1, x2 to xn. These are your unknowns. So then you could say AX equals B is the type of problem which you are looking at, and you want to solve for x. And then, so, when you're trying to look at algorithms for solving this, so of course there's many different ways because do it. And then one that might come to mind as being like very obvious is to say like, okay, well, I know that mathematically it's true that if, assume for the minute that A is invertible, so its determinant is non-zero, and then there's lots of other conditions that are equivalent to that mathematically. But then, so just say A is invertible. Then you could say like, okay, well, if A is invertible, then the way I could get X here is by calculating the inverse of A and then multiplying it by B. And then, so that is a possible way that someone could go about solving this problem. But then this is another important thing with coding is how much time is that going to take to do compared to other alternatives? And so that's actually a big thing about numerical methods is that it's not just about like finding one way to do something. It's about trying to find the most efficient way because as you'll find if you start getting into doing very much with trying to solve physics problems with a computer, you can see that sometimes it starts to get really slow and you want to know the answer. And also sometimes I've had things that like I was running one simulation, it took several days, and then at the end then like maybe there's some error message and then you're like, oh, I waited 3 days for an error message, and then it's like so sad. And then so it's good if you can get them to solve faster, so you only have to wait a few hours for an error message or whatever. Hopefully you get success. But then so in this case, something that we're going to talk about in terms of how do you evaluate how long something's going to take you when you're talking about coding something. And so we're going to refer to something called the number of arithmetic operations. That means like the number of divisions and multiplications and additions and subtractions. And so the reason that that's important is because every time that you do anything with your computer, so you add 2 numbers, the computer had to do something. You subtract 2 numbers, the computer had to do something. So the more and more that you have of those, then the longer your computation time is because the computer has to actually execute more commands. So as magic as computers are, that is still a thing that it is actually doing that takes time. So it's kind of gets rid of some of the magic there when you realize a little bit of how it works. So then it turns out that doing A inverse and then multiplying by B is not as efficient as some alternatives in terms of the number of arithmetic operations. So then this would actually be like the number of arithmetic operations for doing this type of method. Someone calculated and said it's proportional to n to the 4th. So the number of arithmetic operations, I'll write this as NAO, is like proportional to n to the 4th, where n is that n that we have here, so it's the dimension, like the number of unknowns that you have. So you can imagine that if we go back to that case where we were talking about earlier, like say, oh, it's like, and it's 10 to the 6th or something. Well, this is actually quite huge because now you have like 10 to the 6th times 4. So then if you can, so that's actually quite a lot. So if you can decrease that, like even if this was like n, you could just decrease this by 1 order of magnitude. So it might look like, okay, well, I mean, 10 to the 6th times 4 versus 10 to the 6th times 3. I mean, both those are huge. But then be like, well, one of them is significantly huger than the other. So at least you did a lot better. And then so that actually can do a lot for you computation time-wise. So that's a big thing to think about with coding then. And numerical methods is just like, how can I do this in the most efficient way possible, especially if I have to execute something again and again and again and again, so that I can actually get results scientifically in a reasonable amount of time. So that's a worthwhile endeavor. Okay, so anyway, so you can do the inverse method, but there's other ways. And so some other ways are this iteration method. And then there's also elimination methods. And so we'll have to talk about these over a few of these lectures, but let's first talk about an elimination method. So in linear algebra, usually one of the topics that everyone will learn about, probably not too far into the class, is Gaussian elimination. So as you can know from if you have taken linear algebra, Gaussian elimination is something that can be done by hand and for small systems. So again, going back to the same thing. Oh, I could do this by hand, but when the system is huge, I'm not going to. So the computer is still valuable. But this is another point that's really important with coding for numerical methods or for any type of engineering system where you've got a code for it, and it's like you're trying to figure out what algorithm, like trying to figure out how you would code something that has a structure. So one thing that's always really good to do is to kind of write out a simple example that you can do by hand, and then to get a sense of the structure from that. So I think this will make a little more sense as I start going through this. So like when you do Gaussian elimination, say that I just start with a 3x3 system. So in this case, this is my matrix A. And then I have my 3 unknowns, x1, x2, x3. And then I have that it is equal to b1, b2, b3. So here I know that A is the assumption. We're going to write this in a very abstract notation. That's another thing also that's often very helpful with coding is writing things in a general, in a form that you can kind of trace back what you did. So like if you imagine that if you think about this after you see me do it, if the stuff that I'm going to do right now, if I had done it with like actual numbers in here, it would become kind of obscure what I just did. When I look back at my work, I'd be like, well, I don't know, what was my algorithm that I was using? It's a little hard to follow because now all I have is these new numbers and all the positions in this matrix at the end. I don't have it in terms of like the original numbers. So sometimes writing and thinking in terms of abstractions for coding, like in terms of, this is kind of abstract, right? A11, A21, what are those? Those are numbers. But I'm just giving them some like A value, whatever that is, could be anything. But then by thinking in terms of that abstraction, like allowing yourself to say like, that could be anything. And then trying to let yourself think that way, that can be very, very useful for coding. And also another good thing with coding, you really want to try to make it general, because a lot of times what will happen, and especially with solving engineering problems with codes, is that you'll say like, okay, I'm just going to do this one case and then I'm done, right? But then what happens is maybe that one case didn't work like you expected, because that's part of the nature of research, and also physical systems have many interesting things about them. So then maybe it doesn't work like you expected, then you're like, oh, great, now I got to try whatever, with more variables, or oh, I've got to try with this different number. And so you want to give yourself flexibility so that every time you change a small thing, that you don't have to rewrite your entire code. This is all really important to think about when coding these systems. So with Gaussian elimination, what we want to achieve to do Gaussian elimination is sort of the reminder of what happens. You want your system in the end to end up something like A11, A12, A13, and then like a 0 and like I guess A22. I'm going to write prime because these are not going to be the original ones. These are going to be some different ones, but you want this type of structure. And the reason you want this, so x1, x2, x3, and then is equal to b1, b2, again, prime, b3, prime, because the numbers get changed in the process. But then the reason this is useful to get it in this form is because then you're able to say, like, okay, like what this really represents is a system of equations. That's something that's really important to remember, is that this is not like, I think it's very tempting to think of this in terms of like, here is a matrix times a vector times it's equal to some vector, instead of reminding yourself, like, okay, what is this actually? This is saying that this is an equation, this is an equation, and this is an equation equal to these things. They all have to be satisfied at one time. Then, so what this really says is you're trying to get it to the point where you get A33 prime x3 is equal to B3 prime. And then, so then you say, oh, I'm so happy because now what happened is I was able to get x3 explicitly. So you can see right here, I got it in terms of the B3 prime and the A33 prime. And then you go back up, and then now you have the next equation was in terms of x2 and x3 and then known values. So now if you know x3, now you just have x2 is the only unknown in the second equation now. So you move back up through the tiers. And so we call this forward elimination and then back substitution. So then the question becomes like, okay, that's great. So, like I can see like kind of a way that I can solve the problem. So is this a very well-defined algorithm that I could write for a computer in very general form, and then it will do it for me every time? And then so then one thing you can start wondering is like, okay, how might I achieve that final form, and like what steps do I think through when I'm doing that? And then this is where it goes back to this one by writing a small example and writing the steps you would just do if you were just doing math helps you realize what the algorithm is. So what was the algorithm to get to that final matrix that I had before I did the back substitution? So then in this case you say like, okay, well here's what I'm looking for. So if I remind myself, for the sake of making this a little more clear, and then you can always put this back in the matrix form, and that's good. But let me just remind us that we're looking at a system of equations, so why some of these steps make sense. So here are our equations one more time. Oh, plus a33 x3 equals b3. So we are definitely allowed by the rules of, like, if you saw this and someone said like, oh, can I like multiply both sides of this by a constant, or both sides of this one by a constant, you'd say like, of course, no problem. That's the same as that's no problem. Of course you can do that. And then so you'd say like, oh, okay, and if I multiply both sides of this and then I like add these two together, is that still okay? And it's like, well, this side is equal to that side, this side is equal to that side, so essentially you add two sides, then they're equal to the sum. Like, yeah, of course you can do that. So then that's why this step makes sense. So what you have to remember is the tiered form that we're going for. So it would be like, okay, so we already established it's totally fine for me to multiply any of these equations by a constant on both sides, and then for me to add any equations to one another. And I can multiply and then add. Like, I can do these things. It's totally fine. Like, it's from the rules of algebra. So then that's why we had to do those things in the matrix form, which is a lot of times what you'll see. But then, so if you think back to that tiered form where I said like, okay, we're going to do the forward elimination and then back substitution. And then so in the forward elimination, it was a very tiered form where it was like numbers on the diagonal, but below the diagonal, there's zeros. And then so if we think about first like the position here. So there's a number here, there's a number here, here. Oh, sorry. There's also the zero here, zero here. This was the final form. It looked kind of like this. So think for a minute about just this position. So originally we have this A21 would be in this position in the matrix. So then you would say like, okay, I need to get this to be a 0. So then you're like, okay, how will I accomplish this? You could say, okay, well, one way I could get this to be a 0 is if I multiply this equation by negative A21 over A11. So now the coefficient here becomes negative A21, and then I add these resulting two equations together. So definitely that can work. And then, so if I do that, then you'll see that when you make those steps, so if I just do that, I multiply all these terms by negative A21 over A11, and then I add the resulting equation to the second one, then I'll get the result that negative A21 A12 over A11 plus A22 times x2 plus A23 minus A21 A13 over A11 x3 is equal to negative B1 A21 over A11 plus B2. And then, so now the good thing is now I do have a 0 in the x1 position in this. So if I was to go back to my matrix form, now I would have a 0 in the position. If this becomes my second equation, I do have a position, or the first position in the second row now has a 0 in the x1 position. So that's exactly what we wanted. You would go through these similar steps for all the different rows. And then, so I think one thing then that you have to think about, so good, so you could do it all by hand. That's really good. But then what do you get out of this from a coding perspective? So then from a coding perspective, then you look at, like, you think about why did I do that? So if I was to say, like, okay, what was the kind of, like, if I had to think of this in terms of an algorithm, what I did was I said, like, okay, first row is fine. I'm going to leave that row because in my final tiered form, I'm totally okay with having every single one of those positions filled. I don't need a 0 in any position in the first row. Then you go to the second row. You say, like, my goal is to get a 0 in the first position of the second row. So essentially, you're trying to get zeros in all of the positions where it has that the row index, so in that case, it would be like the second position, is it less than the column index? No, or greater than. So it would be the row index here. So this is the 2, 1 position. This is 2, 2, and this is 2, 3. So the column index is going to be this. So I guess you want it where the row index is, number 2, is less than the column index of 1. So for any of those, you want to take it as a 0 in that position. And you can think of that, that's really what's happening on every row. So like you go to this next one, this is 3, 3, so the row position and the column position, this is the only place it's equal. Otherwise, you've got the 3, 2 position, the 3, 1. So every time that you see your row index is less than your column index, now you want to put zeros there. And so by thinking of that in that kind of abstraction, then that lets you say, like, okay, that's like stuff I can start thinking of mathematically and with coding. So I say, like, if I give all of my rows and my columns an index in my code, then I look for cases where, like, this one is less than this one. Then I start, like, taking action based on that. So then that's always really important for the coding. Then the other things that that have to happen is going to be like, okay, so I've figured out, like, under what conditions I want there to be a 0. So then what I need to do is I need to say, like, okay, so for every row, say I look at the second row. Then I say, okay, the way to eliminate my first entry in my second row is to multiply my first row by the negative of the coefficient of my first term in the second row here and divide it by the coefficient of the first term in the first row. Because then that allows me to cancel these out, get the first term here to be negative a21, and then this is a21, and then we have the x1s, and those, when you add them together, they cancel out. And so you can kind of see that this is already going into an algorithm because you're able to identify, like, what was the goal was to get this term here and this term here. So then you can start saying, like, okay, well, I can always identify, like, I can start identifying those terms that I'm trying to put, like, in the numerator and the denominator here in terms of indexes of the rows and the columns. And then so by looking through, so by doing, here's a point. By doing a numerical example that was very small, but that was you were able to do it mathematically, then that allows you to think through, like, okay, what am I doing and why and how can I characterize it in terms of a way that I can actually write in the computer so that I can write something that's repeatable. And so that's going to complete what we're going to talk about today. Thank you for joining.